Okay, right. The graph shown was plotted in an experiment on a metal wire. The shaded area represents the total strain energy stored in stretching the wire. How should the axis be labeled? So one of the key things you learned last week was that I mentioned to you strain energy is actually the area under force extension graph. Okay, so this one here should have been force. This one here should have been extension. So the answer for this is supposed to be A. Yeah, another thing I should probably mention to you is this. What if your graph axis will reverse? What if you get something like this instead? Where instead of force versus extension, this one will give you extension versus force. And then you still get that same straight line here. Now, in cases like this, the strain energy is still area under the force extension graph, but specifically it will be this one. Okay, so bear in mind some of the differences. Strain energy is area under your force extension graph, but depending on how the axes are arranged, you need to be careful about which area you're talking about. If it's just strictly force versus extension, then it's this area. If it's extension versus force, it's this area. Okay, you have to like look at it from here to here instead. Okay, so that's just one thing I should mention to you. Okay, so this is for question 22. Then we move on to the second question. Sorry, second page. Just look at the second page. Page 2. Which is this one. Okay, so we'll clear this one off. Now the variation with applied force of the extension of the spring is shown in this graph. When there's no force applied to the spring, it has a length of 1 centimeter. What is the increase in strain energy stored in the spring when its length is increased from 2 centimeter to 3 centimeter? Okay, so this one here, you still understand the fact that strain energy is area under fx graph, force extension graph. Okay, now when you look at this one, 2 centimeter to 3 centimeter, you may be tempted to say that the area that you want to find is this one. This is actually not correct. Because you see, this one here is the length, not extension. All right, what do I mean by that is that right now your wire, sorry, your spring has a length of 1 centimeter. This is the original length. Let's just say this is L0, okay? But right now they say that your spring has its length increased by from 2 centimeter to 3 centimeter. What it's saying here is that right now you're getting something like this instead. This one is 2 centimeter for the length, and then this one is 3 centimeter for the length. Okay, so this length here refers to the length of the spring itself. It doesn't refer to the extension. So you actually have to find out the extension separately, knowing that your original length is 1 centimeter. So right now, what is your actual length? Sorry, what is your actual extension? It should actually be I'm gonna draw it like this. It should actually be something like this. This one is x1. It will be 2 minus 1, giving you 1 centimeter. And then this one here is x2, it will be 3 minus 1, giving you 2 centimeter. Okay, this is your actual extension of your spring right now. Okay, so rather than finding this area here, which is wrong in the first place, you're supposed to find from 1 centimeter to 2 centimeter extension. So what you need to find is actually this area instead. This is the correct area to find. Okay, maybe I don't do dotted here. I just draw this little thing here. Okay, so this is the correct area to find right now. The 1 to 2 centimeter, from the 1 to 2 centimeter mark. Okay, this is the actual extension of the graph. Right, so this is problem number 2. Okay, this is the actual extension of the graph when the actual extension of the spring, actual extension of the spring when the length changes from 2 to 3 centimeter. So right now, your area is actually the area of the trapezium. Your strain energy is going to be the area of the trapezium. So it will be 2 plus with 4 times with a difference of 1 centimeter. Remember to change it to meter. So multiply by 10 power minus 2. 6 divided 2 times 10 power minus 2. You're going to get 0.030 joules. So answer is B. Okay. Okay, so this one is fine. Then I move on to the next question. If I'm going too fast, hey, sorry, hey, how come we can suddenly join back in? Okay, right. So I'll just move on to the next part. If you are moving too fast, you just let me know, then I'll slow down a little. Or if you need to copy whatever you need to copy and I suddenly rub it, just let me know. Okay, so if nothing else here, then I move on to the next part. June 2015 P12, the next question here. So I'll just clear whatever you have here. Okay, now to determine the Young's modulus of a wire, several measurements are taken. In which rows can the measurement not be taken directly with the stated apparatus? Okay, notice that they've actually bolded this statement here for you. Which measurement cannot be taken directly? In which rows can the measurements not be taken directly with the stated apparatus? It actually just means this. Which measurements cannot be taken or measured directly. Yeah. So to find the Young's modulus, it relates back to the little experiment, which is this one in the notes. Remember, you need to know a bit about the experiment to find out Young's modulus. This part here in your notes under page 6. So there was an equation that you learned that allowed you to plot a graph of force versus extension. That one was actually this one here, where it says Young's modulus is stress over strain, is force over area, and then is extension over original length. So then you get FL over AE, giving you this. Now FL, then this equation here, you can actually expand it a bit further. The force here is actually the weight of a load. So this one will be mg times L. Then this one is talking about circular cross section of a wire. So it's actually pi over 4d square E. Okay, so this is actually the final form if you expand it even more. So right now, for the experiment to determine the Young's modulus, you need to measure these quantities that you have here. Okay, this one or this one. Okay, so let's go through it one by one. If they say you want to measure the cross-sectional area of the wire, can you measure it directly using a micrometer screw gauge? This one area cannot be measured directly. Okay, the keyword here is what measurements cannot be measured directly with the apparatus. If you're talking about area, your micrometer screw gauge doesn't give you the area straight. This one, it only measures, maybe sorry, I use a different color here. This one, micrometer screw gauge, only measures diameter. The area has to be calculated out using A equals to pi over 4 d squared. Yes, it is correct to say the micrometer screw gauge will need to be used in order for you to find the area, but it will not give you the area directly once you use the micrometer screw gauge. It actually only gives you the diameter. And then from there, you need to calculate it out using this equation. So A is actually supposed to be the answer. You cannot take the area, sorry, you cannot measure the area directly using micrometer screw gauge. So to be sure, let's look at the other answer choices. Extension of a wire can be measured using a vernier scale. That is correct. We already saw it here before. The wire, you need a vernier scale to measure the small extension of the wire. Okay, this is correct. You can measure the extension directly. The mass of the load applied to the wire, which is this one, you can measure using an electronic balance. That's correct. Original length of wire, you can use meter rule. That's correct. Original length of the wire is the whole length of the wire. Okay, this is the whole length of the wire. You can actually just use your meter rule. So all this you can measure directly. Only A you cannot. Answer is A. Okay, so this one is okay. Then I move to the next question, the next part. Okay, so I'll clear the drawing. Okay, a long thin wire is suspended from a fixed support and hangs vertically. Masses are suspended from its lower end. The load on the lower end is increased from 0 and then decreased back to 0. The diagram here shows the force extension graph produced. So what you have is a wire with a load there. So you are increasing the force acting on the wire, which in turn gives you some sort of extension. So you gradually increase it, you find out the extension, and then at the same time, you take measurements of the force and extension to give you this graph here. So as you keep loading, after a while, you start to decrease it back to 0, giving you the appearance of this graph here. Okay, so needless to say, this one will be the loading part. This one will be the unloading part. Okay, now where on the graph would the elastic limit be found? Okay, the keyword here is elastic limit. Now notice that there is some permanent extension here. This one here has permanent extension, which in turn will tell you one thing. You now have plastic deformation. You now have elastic limit exceeded. You've actually gone past your elastic limit. All right. So if you recall what I mentioned to you last week, elastic limit is the point to which deformation is elastic. So this. point to which deformation is elastic. Okay, point to which deformation is elastic. Okay, so one thing to note here is that even if material is still loaded exactly to point of elastic limit, deformation remains elastic. Okay, so what I want to say here is that even if you load your material to exactly the elastic limit itself, you are still having elastic deformation. You need to exceed the elastic limit before you can have plastic deformation. Okay, so this one I'll just say here, elastic limit must be exceeded before you can have plastic deformation, i.e. loading must have gone past the elastic limit. Okay, EL here is elastic limit. Okay, I'm just using a short form here. Okay, so let's just look at the answer. Now, when you look at the choice of answer, anywhere between R and S, this one is out. Okay, so R and S here is definitely out. S here you can see is the point where you see from the ground, S is the point where your line stops being a straight line. This one here is actually your limit of proportionality. Okay, the S is the part where your line stops being a straight line, where your force is no longer directly proportional to extension. That is actually your elastic limit. This one here, you could say that Hooke's law is obey up to here only. Maybe I just draw something like this. Up to here, Hooke's law is still obeyed. Okay, so here, point S just tells you is the limit of proportionality. Hooke's law is still obey up to that point. So you see anywhere between R and S, this one is not sensible. Normally, your elastic limit should be after your limit of proportionality. Maybe I should write it here. EL is normally after limit of proportionality. Okay, so one is out. Now, what about the other answer choices just beyond point S? If they suggest that your elastic limit is here, this is your elastic limit, does it make sense? So if you say that it's just beyond point S, just after here, but still before T, does it make sense for this to be the elastic limit? You see, you are loading it all the way to T. If you load it all the way to T, that means you've gone past the elastic limit. So if you've gone past the elastic limit, if you remove the load, obviously you're going to get some permanent extension here. So the answer is B. Okay, this is actually the point where you're supposed to get the elastic limit. Because if it's here, specifically here, you load it all the way to T, that means you've already gone past the elastic limit. So that would explain the graph that you see here. Now, if you say it is exactly at point S, this is wrong because this is actually the limit of proportionality. So this one S for answer part C, exactly at point S, this is wrong. This is limit of proportionality. Now, what about exactly at point T? This is also wrong because remember I told you even if material is loaded exactly to the point of elastic limit, the deformation by right is still elastic. You need to have exceed the elastic limit you must have gone past the elastic limit before you can have plastic deformation. So T is also cannot, so T is not applicable also. Okay, so the correct answer is B. So is that the point T? Yeah. Yeah. Okay. So I've already written the answer there. Okay, so this one is fine. Then I move on to the next part. Okay, this one is a bit difficult. Okay, so I'll just clear everything here. Okay, for question 23, the diagram represents a steel tube with wall thickness W, which is small in comparison to the diameter of the tube. Okay. Wall thickness W, which is small in comparison to the diameter of the tube. The tube is under tension caused by force T parallel to the axis of the tube. To reduce the stress in the material of the tube, it is proposed to thicken the wall. What's the tube with the tube diameter and the tension being constant? What wall thickness will give you half the stress? When they tell you the axis of the tube, this is the axis. Okay, so this is what we mean by the axis of the tube. So what they tell you now is that you apply a tension T here, which in turn causes some stress on the tube. They want you to find out what should be the wall thickness that will give you a stress that is half the value. Okay, so okay, so this one is what you have here. Let me just use a different color to highlight a few things. Okay, so this is everything here. Okay, so now you may be thinking that, okay, if you just look at the tube by itself, this is how it looks like. Where you say that this one is W, and then your diameter is probably two different parts. Eh? Why is it white in color? Your diameter is probably two different parts. You have D in, and then you also have D out. So strictly speaking, you want to find out the stress. The stress here is the force acting over this cross-sectional area. Okay. So if you are talking about the stress acting on the tube itself, what you may have thought would be, okay, stress is force over area. In my case, the force is T. And then my cross-sectional area here would be the area, outer area over the inner area, giving you T over pi over 4 D outer square minus pi over 4 D inner square, and then eventually giving you this. Okay. So now here's where things get a bit difficult, right? So you have two unknown variables here. D0, the outer diameter and inner diameter. If you are very specific now, you notice that your equation is stress is equals to T over pi over 4 D outer diameter square minus inner diameter square. These are the unknowns. Okay, there's nothing in your graph, in your question here that tells you anything about those two. Okay, so it feels like you're gonna get stuck here. You can't proceed any further. This time it doesn't make sense. How are you gonna proceed here? So for this question here, there was a keyword here where they told you that the wall thickness is small in comparison to the diameter of the tube. Okay, what this means is that number one, the outer diameter, because the wall thickness is very small, you see, because they say that the wall thickness is small in comparison to the diameter of the tube. This means that D is very similar to the inner diameter, which in turn will tell you this. D naught is almost equals to Di. You can just equate it to D lah. All right. And then from here, you can also do something else, where we tell you that because the wall thickness is very small in comparison to the tube, that means the tube can be approximated. Sorry, the color is a bit odd, right? Let me use a different color. You can say that the tube can be approximated as a flat sheet. Okay, because the diameter is so much bigger than the tube. Sorry, the diameter is so much bigger than the wall thickness itself. You can actually think of this tube as being similar to a flat tube. What I mean by that is that you can imagine cutting this tube in half right over here and then laying it flat so that it now looks like this. Okay. So you cut the tube in half across, then after that you can lay it flat. It will become a flat sheet. Okay. So from here, your area is now this already. And this is now your new area. This is your area, which is equivalent to this. Okay. They are same. The area is the same. But this makes your calculation a lot easier. Because now what you can see here is that this one here is actually my W. And then this one here this one here, length L, is actually the circumference of circle. Okay, because you can imagine that this entire length here is actually the circumference of your circle. So circumference of a circle, you learn it as pi d. Okay, so this one is now another way of looking at this same question. So you try to use stress equals to force over stress is equals to force over area here, you're going to get something like this. Stress is force over area, which is T over W times pi d. Therefore, stress is T over pi W d. Okay. Now, the question says that the tube diameter and the tension being constant will mean that T and D constant, stress is actually just going to be inversely proportional to the thickness. Thickness is W here. Okay, where's the thickness? Yeah, this is the W, the thickness is this one. This one is the thickness. Okay, so you get to this part, T and D being constant, that means T is inversely proportional to W. So you want half the stress. What should the thickness be? So if your stress is reduced by half, wait on, let me just fill this one more. I use a different color. Okay. This one, if your stress is reduced by half because you want half the stress, That means W would need to increase by 2 times. Okay, you see the relation here is this. Stress is inversely proportional to width, is inversely proportional to the thickness. If stress reduced by 2 times, that means width must increase by 2 times. Sorry, the thickness must increase by 2 times. Therefore, your new thickness is 2W. So therefore, new thickness is 2W. Okay, so this is the answer for this one. This is one way of looking at it. There is also another way of doing the same thing. I will just tell you both methods. This one I'll just write it at the top right hand corner. Using a different color. I'll use this one. If stress is inversely proportional to thickness, you can also say this. Stress 2 over stress 1 is going to be equals to 1 over thickness 2 over 1 over thickness 1. So eventually, stress 2 over stress 1 is thickness 1 over thickness 2. So if your stress is reduced by half, that means stress 2 is half of stress 1. So you get this one. Okay. And then after that, I can say that your W1, yeah. Okay, I'll just leave it as this. And then you get this. Okay. Half stress 1 over stress 1 equals to W1 over W2. This will cancel off. Eventually, you get this conclusion that W2 is actually 2 times of W1. Okay. You'll be getting the same answer as this also. Same. Okay. So when it comes to this kind of questions, this method of doing things using ratios, you will see a lot in chapter 7 onwards. Under deformation of solids, from the chapter of deformation of solid onwards, you will tend to see quite a number of questions that will need you to make use of ratio. This is what we call as ratio method. You need to find some sort of relation, something is proportional to something or something is inversely proportional to something. If one of the quantity changes, what happens to the other corresponding quantities? You can either do something like this, or you can either do something like this. Okay, there are two different ways of finding the same answer. But frankly speaking, the first method is actually much easier lah. The second one is a bit more tedious, that's all. Okay, so this one is okay, then I will just clear everything off. So I'll clear everything up. I'll just clear it. Then we move to the next one. Okay, when ice melts, it contracts. Which rule is correct for ice turning into water? This is not in your syllabus anymore. Okay, states of matter, and then things like boiling, evaporation, freezing, condensation, etc. This is no longer inside your syllabus. Okay. Molecular arrangement and stuff. Molecular arrangement, motion, and spacing is also not in your syllabus. Okay. So in general, you see something about things that talk about solid, liquid, gas, boiling, evaporation, freezing, condensation, and then how the molecules are arranged, what's the spacing, and what's their motion. This one is under the old syllabus in 2016. It was in the syllabus before 2016, but after 2016, it has been removed. So this one here, I accidentally included it in. This one don't need to do, okay, because it's not inside the syllabus. Okay, so this one is not in syllabus, don't do. So what I want to do is the next question, question 22. Okay, the steel bar of circular cross-section is under tension T as shown. The diameter of the wide portion is double the diameter of the narrow portion. What is the value of the stress in the wide portion and to the stress in the narrow portion? Okay, so this is the wide portion. This is the narrow portion. Okay, so notice that they didn't give you any values. Again, they ask you to find some ratio. So steel bar of circular cross section is under tension T. Diameter of wide portion is double the diameter of the narrow portion. What's the value of the stress in the wide portion versus the narrow portion? Okay, what this one you need to do is you do something like this. The equation for stress is force over area. This one will be T over pi over 4 d squared. So stress is actually T over pi over 4 d squared. Now, you need to use the method similar to what I just taught you. When it comes to finding ratios, you need to use ratio method, okay? So if I'm talking about the wide portion and the narrow portion, notice that the T is the same. For the wide portion, you're still experiencing the same T. For the narrow portion, you're also still experiencing the same T. The only thing different is the diameter. This one would have probably diameter dW. This one is diameter dN. Okay, but the thing here is that the diameter of the wide portion is double the diameter of the narrow portion. This means that dW is 2 times of dN. Okay, so how do I proceed? When you want to use ratio method, you number one, find out the equation that relates both cases. Okay, find out the equation that relates both cases. In this case, it is this one. And then what you do next is that you determine what is the same, or i.e. constant, for both cases. So that it can be eliminated from equation. Okay, what do we mean by that? Okay, this one is for part 1. Find out equation that relates to both cases. This is this part here. The part where I say you then need to determine what is the same or constant for both cases so that it can be eliminated from the equation. Notice that just now I mentioned to you that for both cases the tension is the same. So what you would do here is that T here being constant, you can now find out a new relation. T is constant, that means stress is directly proportional, sorry, not directly proportional, inversely proportional to T squared. This one is constant, sorry, T is constant, you can eliminate it. Pi over 4 is also a constant, you can eliminate it. The only one that's left is this one. Okay, so you say that stress is inversely proportional to D squared. Yeah. So after that, then you work out the relation. Then you work out the new relation and solve. Okay. This is actually for this one. Okay, so let me just write this. T is constant, stress is inversely. Yeah, this one will be the part 3. This is for the. This part here is the new relation. This part here is you finding out what is constant. Okay, so that is what I meant by ratio. When you want to use ratio method, it's generally these three steps. Find out the equation that will relate to both cases, and then find out what is constant for both cases so that you then can eliminate it from the equation. And then lastly, work out a new relation and solve the question. Okay, so now when it comes to the solving part, I'll just write the workings here. So there are again two different ways of doing this. I will just show you the two different ways. If stress is inversely proportional to d squared, now you see dw over d1. Okay, yeah, this one no need to, I think. Oh, because they want the ratio stress. Sorry, this one no need. Forget what I said. I'll show it to you later. Okay, now this one, they want the stress in the right portion to stress in the narrow portion. What you can do is that since you know that the relation is the stress is inversely proportional to d squared, you can now say that stress over the wide portion over the stress in the narrow portion is equals to 1 over dw square 1 over dn square. So eventually you will get dn square dw square. And this is the new relation. This is the exact equation now. But then you know that dw is 2 times of dn. So what you do is that you sub in the values now. Where you say that it's still dn square here. dw is 2 times of dn square. Remember to square the entire term, so you are going to get dn square 4dn square. The dn square will cancel off. Your answer would be 1 over 4, giving you 0.25. Answer is A. Okay, so this is the way you will do this question. Okay, so answer is A, because this is 1 to 4. Yeah, 1 to 4, so 0.25. Okay, so this one is fine. Then I'll move on to the next question. Okay, so this one is okay. Then I'll move on now. Okay, the next question. The graph shows the non-linear force extension curve for wire made from a new composite material. Composite material is just something, it's just a material that's a combination of metal and non-metals. Okay, composite material is a material that's made out of a combination of materials, metals and non-metals. If it's an alloy, then it's made out of a combination of metals only. Okay, but that is something else. What could be the value of strain energy stored in the wire when it's stretched elastically to point P? Okay, so this one here, we need you to do a bit of common sense. So as I mentioned to you before, strain energy is area under Fx graph. So by right, it should be this one here. Okay, but this graph is not a straight line graph. It is a curve. So right now, what is the value of the strain energy stored in the wire when it's stretched? You do know, yeah, you will find the area under the graph, but then you're limited in the sense that this is not a uniform shape. It's not an exact triangle. It's a curve. So you do the best you can. You try to see, imagine that there is a triangle here, from here to here. You try to find this part first. So this one here, strain energy is going to be the area under the area of the triangle. It will be 100 times with 2 millimeter change to meter. You're gonna get 0.10 joules. Okay, now when you do up to here, then you see, isn't the answer here already? Then you may be tempted to just write this as your answer. This is wrong, okay? Because this one here is actually the minimum strain energy, okay? This is not the actual, because if you look at the graph, what you're finding is actually just this portion here, the triangle here. You still have a small part that you haven't taken into account, which is this one. Let me use a green one. Okay, this has not yet been considered. So if you say that, oh, 0.1 joule, this is the answer, this is not correct. Okay, this one out. Okay, this one is out also, definitely. This one here, I'll say that this is wrong because still some air energy has not been considered. Because some energy still hasn't been considered, sorry. So, been considered. Okay, because some energy hasn't been considered, which is actually this green part here. Okay, so B cannot be the answer. You need something more. Okay, so the actual strain energy should be more. Actual strain energy should be more than 0.10 joules. So then you see that you have two choices of answer. Either this one or this one. Okay. So how do you pick which one is the correct one? So if you see 0.20, this one is double of 0.10 joules. This is actually too much. Because you see, the error that you haven't really considered is just this small portion here. Okay. So this small portion here, this small area here represents a small amount of energy. It's no way going to be the same as this one here. Okay. If you say 0.20 joules, that would mean that the area you haven't taken into account is as large as the one that you just calculated. Only then would you have close to double, only then would you have double the energy. So this one is actually too much. It cannot be the answer. So answer this one is wrong. So the only sensible one will be C. Because you see this one only is plus 0.01 joules out of 0.1 joules. It's only added 0.01 joules to the 0.1 joules here. So this is reasonable. Because you have a small area, you expect to have a small amount of energy. So the actual one should be slightly more only. Okay. This one is plus 0.10 joules. This is too much, no? Okay. So D is wrong. Correct answer is C. Right. So this part is okay. Then I'll move on. Okay, so I clear all whatever you have here. Okay, now this one here, the diagram shows the stress strain graph for bone. What's the Young's modulus of bone? So stress strain, this is stress strain, not force versus extension. Recall that earlier I mentioned to you in the notes, if you're given a stress strain graph under page 8 of your notes, if you're given a stress strain graph, gradient is actually your Young's modulus because it is stress over strain. So right now, this one here, what you do is that you find the gradient of your graph. Young's modulus is equal to the gradient. All right. So you consider only the straight line portion. When it comes to finding spin constant and Young's modulus, always consider only the straight line portions of the graph, which is this one. Okay. So this one, your stress versus strain, your gradient would be 2 times 10 power 6 minus 0. And then this one will be, okay, bear in mind this is in percentage form. This is in percentage. This is already in percentage. You need to change it to number. You need to get rid of the percentage. So this one is actually 1.5 divided by 100 minus 0. If you're taking between these 2 points, so it'll just be 0. It's 2 times 10 power 6 divided by 1.5 over 100. You're gonna get 1.33 times 10 power 8 Newton per meter square. Am I correct? Sorry, my mistake. I took 1.5 right? No, I'm talking about this one. I should have took 1. Sorry, my mistake. Not 1.5. This one is 1.0. Okay. So 1 divided by 100, 2 times 10 power 6 divided by the answer. You will get 2 times 10 power 8 Newton per meter, which is answer D. Okay. Now this one here, because I minus 0, I minus 0, it's actually 2 times 10 power 6 divided by 1.0 divided by 100. It's actually just the same as me taking from a point. Okay, this one is just like me taking a value of stress as, wait, now let me just explain a little for this. What I just want to highlight to you here is that when finding gradient of a line that starts from origin, the value is the same as when point substitution is used, single point substitution is used. The value is the same as when single point substitution is used. Okay. So let me just explain this a little to you. If you're finding the gradient of a line that starts from origin, the value is normally the same as that of a single point substitution. Right, this one here, you see, is me finding the actual gradient. Okay, this is actually finding gradient. Okay, sometimes in your marking scheme, or sometimes if you are taught by a different teacher, you might notice that your teacher doesn't take the gradient. Instead, he just take a point. Here, I know that this point is 2 times 10 power 6. This one is 1.0%. Some teachers will just say, okay, you just take any point on the graph. You just say take maybe this point, and then you say that E is stress over strain is 2 times 10 power 6. Then it's 1 divided by 100, giving you 2 times 10 power 8 Newton per meter square. So this is actually just what I mean by single point substitution. Okay. All right. You might notice that sometimes I say it's gradient, but then after that, you see the marking scheme and all, they don't really find the gradient. They actually just use a single point substitution, meaning to say they find the value of a single point and sub it in. It's actually the same thing, okay? Because if it is gradient of a line that starts from origin, it's actually the same as you doing single point substitution. Like the ones that you see here, you see this one here, because it starts from 0, this one will actually just cancel off. I mean, it doesn't cancel off. The 0 is just nothing there. In the end, it gives you something like this, which is the same as this, which in turn is going to be same as this.